Greetings, everyone. I'm Yatharth Singhal, and today I will be presenting our paper titled Thermal in Motion, Designing Thermal Flow Illusions with Tactile and Thermal Integration. This work was done in collaboration with Daniel Honrales, Haokun Wong, and my advisor, Dr. Jinre Kim, from the University of Texas, Dallas. Consider a scenario where temperature feedback in virtual world isn't static, but moves dynamically across your skin just as it does in real life. We could deliver moving cues to various parts of the body, like palm, torso, back, or arm, just to name a few. This is the essence of our vision, moving thermal cues in VR. One of the key challenges with current thermal feedback systems in VR is that they are static. This static nature limits the richness of virtual interactions, preventing users from experiencing the natural and dynamic way temperature behaves in the real world. Well, to provide dynamic thermal sensation, the simplest approach would be to use a large number of thermal actuators and activate them sequentially. However, while this solution is conceptually simple, it requires a large number of thermal actuators that can complicate the setup design and lead to feasibility issues. So what if it was possible to provide dynamically moving thermal cues with minimum or even just one thermal actuator? Introducing thermal in motion. Thermal motion is an illusion of flowing thermal sensations achieved by integrating thermal and tactile actuators. It is a perception-driven approach that utilizes two perceptual illusions: vibration-induced thermal referral and apparent tactile motion. The illusion of vibration-induced thermal referral is what supports the thermal part of our dynamic feedback. This illusion states that whenever a thermal and tactile actuators are activated simultaneously on a nearby location on the skin, the thermal sensations are also perceived at the tactile location. By leveraging this, we can deliver heat sensations to any tactile actuator in an array. To provide the moving effect of our dynamic feedback, we utilize apparent tactile sensations. Apparent tactile motion suggests that when two vibrotactile stimuli are placed close together and activated in quick succession, they are perceived as one single actuator moving between them. By using apparent tactile motion, we can create the illusion of a moving tactile point. Then, by applying thermal referral, we transfer heat to this illusory moving tactile point to create the perception of a moving thermal cue. And we do this by utilizing multiple tactile actuators and only one thermal actuator. So we've established the illusion for thermal motion. Now, how do we define the motion itself? Well, our algorithm has three key components. First, we create a perception of continuous tactile motion. This is done by varying intensities and activation timings of multiple vibrotactile actuators. Next, the second part is we apply intensity smoothing, where each tactile actuator gradually rises and falls from its maximum intensity. Easing actuators in and out of activation transfers sensation better and makes the motion feel smoother and continuous. And the last part of the last component is warm-up. In our initial tests, we observed that thermal sensations were hard to detect at the beginning of the motion. This is possibly due to the slow onset time of thermal feedback. To fix this, we added warm-up phase before the actual motion begins. During this phase, we activate the thermal actuator and the first tactile actuator simultaneously to allow thermal referral to establish early on. We conducted 3 user studies to verify our approach. In the first study, we investigate whether thermal motion can create a clear and continuous sensation of moving thermal cues. We also look at different factors that influence thermal motion and determine which one of them has the biggest impact. We conducted a study with 16 participants focusing on 3 key factors: temperature, thermal actuator placement, and tactile motion direction. We tested both hot and cold sensations by selecting 4 different levels: +9, +6, -12, and -15 degrees Celsius from their neutral skin temperature. We call these levels hot, warm, cool, and cold, respectively. We examined the best placement for thermal actuators by positioning it onto 3 different locations: the middle, the wrist, and the elbow. We tested 2 motion directions, from wrist to elbow and from elbow to wrist. For each trial, participants were asked whether they could perceive the signal, whether they could perceive the thermal cue moving along their forearm as a single continuous stroke. Our results showcase that overall, participants perceived thermal motion more than 75% of the time, while some conditions reaching over 90%. For temperatures, the hot temperature condition demonstrates the highest performance, with thermal motion perceived over 90% of the time. Moreover, we found that extreme temperatures like hot and cold showcased a higher likelihood of perceived thermal motion as compared to cool and warm cases. We also observed that positioning the thermal actuator in the center of the forearm yielded the highest likelihood of perceiving a clear and continuous thermal motion. Finally, both the direction showed higher chance of thermal motion perception, but we did not observe any significant differences between them. Thus, this study shows the viability of thermal motion perception, with the best results coming from placing the thermal actuator in the middle and using extreme temperatures. The second study focuses on temporal thresholds of the motion. We observed that duration of the motion is key to creating a good and optimal thermal illusion. If the duration is too short, the temperature is only felt at the starting point. If the duration is too long, then people perceive tactile motion and they perceive thermal feedback only on the actuator location. Thus, there exists an optimal range of duration where thermal motion is best experienced. In this study, we calculate the range for both hot and cold conditions and study how temperature affects this range. We conducted the study with 16 participants and used a 1 up 2 down staircase method to determine duration thresholds. We calculated the lower and upper thresholds for hot and cold conditions, and thus resulting in 4 staircases per participant. We found that the optimal duration range for hot condition to be between 1.9 to 10 seconds. Since the distance of the motion is constant in our setup, which is 18 centimeter, we can convert it to speed, which would be 1.8 to 9.5 centimeter per second. For cold condition, we found that the motion was well perceived between the speeds of 2.4 to 5 centimeter per second. Now, this is interesting as it shows that the optimal range for hot temperature is almost double to that of cold. And finally, we conducted another study to investigate the effect of thermal motion on VR user experience. For this, we fabricated a sleeve interface and asked participants to interact with 2 virtual scenarios. A social touch scenario where participants found themselves seated on a table next to an NPC. The NPC then proceeds to stroke their forearm while thermal motion plays concurrently. And the second scene, which is set in a futuristic environment where participants can collect ice and fire powers on their virtual sleeves by interacting with blue and orange orbs. Once they charge their sleeves, they can make a gesture to shoot these orbs by discharging it. Depending on which orbs they interact with, they will experience a hot or cold motion. We interviewed participants after they interacted with each scene, and overall, participants reported that thermal motion sensations from the sleeve greatly enhance their immersion in the VR environment. These sensations also improve their understanding of interactive elements, and they highlighted high level of realism.
Let's see.
Okay, I'm almost done. So I think I can continue from here. Yeah, I have the charger. Yeah, I have my charger right there, but can I plug it here?
Sure. Yeah, sure. Yeah, just very quickly. It's going to get some more juice here. As a reminder, I've heard that this paper also has a demo in the demo session later tonight. So I'd highly encourage everybody, check out the interactive demos. I will definitely be there, and I highly encourage. I think Jazz's paper has a demo as well. There's going to be fantastic demos there tonight.
Yeah. starting.
Just bear with us for one more second.
Well, I hope it's not updates.
Any final, do you have just a few final thoughts possibly?
Yeah, just the last.
Okay.
I'm just going to continue. Oops. I have just like a couple of slides.
Okay.
Okay, so sorry about that. So we interviewed participants after they interacted with each scene, and overall participants reported that they felt high levels of immersion, enjoyment, and realism, and mentioned that this experience exceeded their expectations. In this work, we introduced thermal motion, a method to provide dynamic thermal cues by thermal and tactile integration. We leveraged this perception-based approach and to reduce hardware demands. We defined thermal motion and identified key factors and optimal parameters for providing clear and continuous thermal motion. We demonstrated that we can enhance VR experience by integrating thermal motion within. So we are also presenting this work as a demo, so please visit us in Lobby 2. And thank you for listening to my talk and being patient. Please feel free to ask any questions.
All right, thank you so much. Let's have time for one quick question, and then our authors will also be kind of at the poster sessions just after this, as a reminder.
Hey, great presentation. I'm Will from CMU studying HCI. I was wondering if any of the participants, did you break the illusion with them, and once they understood the underpinnings of the technology, did you see decreased results or decreased effectiveness, or did you not look into that?
That's a great question. Thank you for that question. The illusion actually depends, it varies from perception to perception. But for our study, we did not really had any other participant that could not feel the illusion, but it's possible to do so if we do not use optimized temperatures and optimized tactile intensity. So the illusion also depends on how strong the thermal that they feel. Because if the thermal is too strong, then they will always feel it the actual location, the real location where the thermal actuator is. So we need to keep those things in mind. Yeah.
Thanks.
Thank you.
Okay, let's thank our speaker here one more time.